communication across an organization. Not all peers can do this, but these are special peers who are only authorized to do so, which are nothing but anchor peer. The anchor peers are defined in channel configuration. Leading peer. Leader peers are those who communicate or disseminate messages from ordering service to other peers in the same organization. These peers use gossip protocol to make sure that every peer receives the message. Leading peers cannot communicate across an organization. If any leading peer is not responding or is out of network, then we can select a leading peer from available peer based on voting or randomly chosen one. And now, another important component, which is orderer. In a blockchain network, transactions have to be written to the shared ledger in a consistent order. The order of transactions has to be established to ensure that the updates to the world state are valid when they are committed to the network. Unlike the Bitcoin blockchain, where ordering occurs through the solving of a cryptographic puzzle or mining, Hyperledger Fabric allows the organizations running the network to choose the ordering mechanism that best suits that network. This modularity and flexibility make Hyperledger Fabric incredibly advantageous for enterprise applications. Hyperledger Fabric provides three ordering mechanisms: Solo, Kafka, and Simplified Byzantine Fault Tolerance, or SBFT in short. Please note that SBFT has not yet been implemented in Fabric. What is Solo? It is the Hyperledger Fabric ordering mechanism most typically used by developers experimenting with Hyperledger Fabric networks. Solo involves a single ordering node. In this, the transactions are ordered in chronological order to form a block. And what is Kafka? It is the Hyperledger Fabric ordering mechanism that is recommended for production use. This ordering mechanism utilizes Apache Kafka, an open source stream processing platform that provides a unified, high throughput, low latency platform for handling real-time data feeds. In this case, the data consists of endorsed transactions and read-write sets. The Kafka mechanism provides a crash fault-tolerant solution to ordering service. Other components which are part of the network and yet very important to understand are as below. Channels. The Fabric network can have multiple channels. Channels allow organizations to utilize the same network while maintaining separation between multiple blockchains. Only members or peers of the channels are allowed to see the transaction created by any member in a channel. In other words, channels partition the network in order to allow transaction visibility for stakeholders only. Only the members of the channel are involved in the consensus, while other members of the network do not see the transactions on the channel. The peer can maintain multiple ledgers and peer can be connected to multiple channels. Identity. Each actor in a network, peer, orderer, client, admin, have some digital identity in the form of certificate X.509. This identity is used to verify at each and every step of a transaction in order to check if the source of the transaction is from a valid source. In addition to the multitude of endorsement, validity, and versioning checks that takes place, there are also ongoing identity verification happening during each step of the transaction flow. Policies. Policies reside in the channel configuration, but in some cases, it resides in chain code too. To define, a policy is a function which accepts as input a set of signed data and evaluates successfully or returns an error because some aspect of the signed data did not satisfy the policy. There are two types of policies: signature policy, that specifies policy as a combination of evaluation of rules for MSP principles and implicit meta policy that aggregates the result of evaluating policies deeper in the configuration hierarchy, which are ultimately defined by signature policies. A ledger. It is a current state of the business as a journal of transaction. A ledger consists of two different parts, a world state and a blockchain. A ledger is kept at all peers and optionally as a subset of orderers. The two different parts of ledgers are world state. Each chain code has its own world state and blockchain. It is a database that holds the current state of the ledger state. These states are expressed as key value pairs. It holds the fact of a business object. It cannot be created, updated or deleted. When application submits the transaction and when it comes to committing the valid transaction, it first commits in the world state and then it is updated in ledger. State also has a version number. This version number changes each time the state is updated. When the ledger is created, the world state is empty, as any transaction which represents a valid change in world state is recorded in blockchain too. This means world state can be generated at any time from the blockchain. This state is maintained by peers only. Blockchain. A transaction log that records all the changes that have resulted in the current world state. Its data structure is different, as once written cannot be removed. It is immutable. It is a historical record of facts about how the objects arrived at the current state. It is structured as a sequential log of interlinked blocks, where each block contains a sequence of transactions and each transaction representing a query or update to the world state. Each block header includes a hash of block transactions as well as a copy of a hash of the previous block's header. Blockchain is always implemented as a file, not like that of a world state which uses a database. The first block in the chain is the genesis block. Though this is starting point of the ledger, it does not contain any transaction details. Instead, it contains configuration transaction details containing initial state of the network channel. This diagram shows what each block consists of. And this diagram shows what each transaction in a block consists of. It's very important to spend some time on these diagrams because they show you the structure of a block and a transaction in a block. Chain code or a smart contract in Fabric. A smart contract defines the transaction logic that controls the life cycle of a business object contained in the world state. It is then packaged into the chain code which is deployed to the blockchain network. Smart contracts are defined within a chain code. Multiple smart contracts can be defined within a single chain code. When a chain code is deployed, all smart contracts available within the chain code is made available to the application. We can see that a smart contract is a domain-specific program which relates to a specific business processes, whereas a chain code is a technical container of a group of related small contracts for installation and instantiation. Every chain code has endorsement policy attached to it, which applies to every smart contract defined within it. This identifies which organization must sign a transaction generated by smart contract in order to consider it valid. So, in short, every smart contract has an endorsement policy attached to it. A smart contract can call other smart contracts within a channel or across different channels. For the purpose of this course, what we have learned on Hyperledger Fabric is good enough. For those of you who want to get into further details, please go through the following links that will help you to understand the transaction flow in detail. The links are here.